Hello everyone, welcome to my talk. My name is Kelly Hao and I am an upcoming assistant professor at Georgia Tech. Today I'm going to talk about the software hardware co-design for multi-modal multitask learning in autonomous systems. Of course, this is not limited to autonomous system, but is also a general formulation for this typical software hardware co-design problem. This is a collaborative work between Georgia Tech and UAUC with Professor Zhenmin Chen, and I would like to thank Professor Jingtong Hu from Pittsburgh and Professor Pan Li from Purdue for their insightful discussions. This page shows the outline of today's talk. So first, I'm going to introduce what is MMT, multi-modal multitask learning, and especially their applications in autonomous systems. And second, let's discuss why we exactly need software-hardware co-design for MMT, especially when we're targeting these heterogeneous platforms. And third, we will discuss how to formulate and how to solve this typical co-design problem. Now let's first talk about what is MMT. So first, what is multimodal learning? The concept of modality means the way in which data is presented. For example, we have text, visual, vocal, point clouds data, and they're all presented in different shapes and formats. So they are different formalities. And multimodal learning wants to build models that can process and relate information from multiple modalities and make decisions together. So here are different aspects for multimodal learning. For example, modality representation, translation, data alignment, model fusion, and co-learning. And in the scenario autonomous system, we'll mostly focus on this modality fusion. Here are 3 examples of modality fusion. In the first example, the model is combined with this visual information and depth information into a combined multimodal learning system. And the second one is combining image input and speed information into this combined model. And this third example is combining the radar data and image data into this combined model. So actually, different multimodal learning in autonomous driving are utilizing different sensor fusion approaches, including early fusion, mid fusion, late fusion. And in this right figure, we are illustrating the architectures of different fusion methods. For early and mid fusion, these different data modalities are converted into a joint representation and processed for decision making. And in this late fusion, all the modalities are processed independently before they reach this final decision making. Of course, different approaches, different fusion approaches, both have their pros and cons. For example, early fusion may save computing through parameter or weight sharing. But how about their accuracy? This is really something we care about. Now let's take a look. So this is one example work that is studying the different impacts of early and late fusion for RGB data and this depth data. So they tried 3 different fusion methods: early fusion, mid fusion, and late fusion. Now let's see how they work. So interestingly, in this work, they have found that in the most of the cases, the early fusion scenario results in better accuracy than the mid fusion and late fusion. So apparently in this work, they advocate for early fusion of RGB and depth information. This is another example. This work also compares the early fusion and late fusion for camera image and LiDAR image. And from this table, we can see that actually in this work, the late fusion shows better results than early fusion. And here, the green line is the late fusion. So interestingly, in this work, they are advocating for late fusion of RGB and LiDAR data. So from these examples, I think one takeaway from multimodal learning is that we have different advantages and disadvantages of early, mid, and late fusion, and they're really case by case. And also the specific application and the fusion architecture really is important and they matter. So maybe one idea we want to use is to use an automated approach to design the multimodal fusion architecture. So this is a technology called Neural Architecture Search, short for NAS. I think it's a really popular and famous term to most of you. And in the right side, I'm showing an example work that is utilizing NAS to search for a multi-modal fusion architecture. So this is modality X, this is modality Y, and here in this box, they're trying to search for the best way to decide when to fuse and how to fuse. So till now, we have introduced multi-modal learning. Now let's take a look at the multitask learning. So multitask learning is to learn multiple related tasks jointly to enable knowledge transfer, to improve generalization performance, or to mitigate training data sparsity. For example, we have one task with very scarce label data and another task has sufficient data. So maybe we can borrow some knowledge learned from that task and to use that to train this one. So this is why we're interested in multitask learning. This figure shows two typical multitask architectures. One is called soft sharing, that they're not actually sharing the parameters, but by adding some constraints. And this one is all the tasks are actually sharing some layers and maybe feature maps. Now let's take a look at some real examples of multitask learning. So this is one example, not exactly in autonomous driving, but related. So in this case, they're trying to learn 3 tasks at the same time: odometry learning, global post learning, and the semantic segmentation. So here we can see that they are enabling these feature sharing across different tasks. So based on our experience on multimodal learning, probably we can already guess that multitask learning also has a large design space when we want to decide what to share, when to share, and how to share across different tasks. So again, here, neural architecture search, NAS, can also be a promising solution to find a good multitask learning architecture. Here are 2 examples. The first one is trying to find the best sharing method across these 2 tasks at each point, whether they should be sharing information or not. And the second one is also a multitask learning for these 4 tasks, A, B, C, D, and they're trying to decide when to split the backbone for each individual tasks. So basically, the first one is trying to decide how to share, and the second one is trying to decide when to share. So the main takeaway here for multimodal multitask learning is, of course, first, MMT is really promising, but it's very hard to design because it has a large design space. And we also demonstrated that NAS might be helpful, and we have already seen that NAS can help find a higher quality MMT model. Well, but there is always a but, that we can see that these MMT models, usually the ones found by NAS, usually have complicated structures. And here I'm showing some examples. Some of them are manually designed and some of them are found by NAS. So we can see that they are really different in terms of number of layers, how they're sharing the data, and how the connections are constructed. So the next question we are going to ask here is how these MMT models perform on hardware, because we not only care about their accuracy, we also care about their hardware performance in real applications. For example, in autonomous driving, we really care about the end-to-end latency in order not to kill people. So especially when we are mapping these MMT models on complex heterogeneous platforms, which we call HTP for short, their performance is really hard to predict or to guarantee. So in the next few slides, we will discuss exactly why we need this software-hardware co-design for MMT, especially when they are mapping to these heterogeneous platforms. And we will show you that these MMT on heterogeneous platforms really significantly complicates the design space. Now let's first take a look at some heterogeneous platform examples. This is one heterogeneous platform example from Xilinx, their latest ACAP architecture. So this is really something heterogeneous. We can see that there are scalar engines, there are adaptable engines built by programmable logic, and they have dedicated AI engines and also DSP blocks. So these different components talk to each other using network on chip, and they have different protocols and interfaces for external communication. So this is one example. And this is another example from Tesla. This is Tesla's full self-driving Asic. Now let's take a look at the right side. This is also something heterogeneous. We have 12 CPUs, 1 GPU, and 2 neural network accelerators. And also they're talking to each other using this network on-chip controller. So far, we have shown that these MMT models can really be complicated and the platform can really be heterogeneous. And now let's take a deeper look at how do these MMT models perform on these heterogeneous platforms and how do they complicate the design space. Let's take one example from this multitask learning result from CVPR 2020. And this model, this multitask model, is searched on 2 tasks by NAS. And the task fusion is done by going through a concatenating layer and going through a one-by-one convolution. So this is the MMT model, and this is the heterogeneous accelerator used in our simulation. So here we are imitating the Xilinx ACAP architecture. So we're also using the network on-chip as the communication, and different accelerators are grouped together with shared buffers. So of course, you can use your own HTTP for simulation or for future search. This page shows 3 different mappings and different MMT architectures. Let's take a closer look at this part for now. So this is the first mapping. These 2 shapes represent the first task. These 2 shapes represent the second task. And the colors mean which accelerators they are mapped to based on this heterogeneous platform. So in the first mapping, we can see that the total latency is 6 units. For simplicity, we're not showing the exact number of clock cycles, but in a cursor evaluation for latency. So the data movement across these 2 groups of accelerator is 6 as well. And this is the second mapping. And actually, we are switching some of these mappings. And in this case, we can see that we're not changing the total number of latency, but we are reducing the number of data movements from 6 to 3. This actually can be really beneficial. And in the third example, we tweaked the model by removing one of the fusion operations. And here is the accuracy change. Comparing with the previous one, we can see that we suffer from less than 1% accuracy loss, but we achieved a much more hardware-friendly MMT model structure and mapping. So here we have a total of 5 unit latency, and the data movement is actually only 2 across different groups. So based on the previous motivating example, we have seen that MMT models are really promising but complicated, and combining with their mapping on the heterogeneous platform, this is actually a typical software-hardware co-design problem. That how we can both design the MMT model and determine their mapping on the hardware at the same time. So next, we are going to talk about how to formulate and solve this co-design problem. Of course, this software-hardware co-design is not something completely new, and we have a bunch of existing and excellent works trying to do it. For example, we got some great inspirations and ideas from darts, NICE, and EDD. For example, these darts is one representative work talking about differentiable neural architecture search algorithm, and they're trying to search for a good software architecture for high model accuracy. And this nice work, neural architecture and implementation co-search, well, is actually proposed by us, and we're trying to extend from NAS to cooperate hardware implementation search. And this is a prototype. And then this EDD work is an actual co-design algorithm following this nice idea. So it's a differentiable DNN architecture and implementation co-search. So now let's see how we can utilize these interesting ideas and inspirations and try to adjust and apply them to our new and more complicated problem here for this MMT and heterogeneous platform co-design. So the core idea and major inspiration from NICE and EDD we can borrow is that we have 2 design spaces, the neural architecture search space A and the implementation search space I. what we want to do is to merge these A and I together into A and I. So, and if we're lucky enough, we can formulate this merged design space A and I as differentiable. And then we can use some elegant algorithm, for example, gradient descent, to explore this merged design space. So this is the core idea, and now let's see how they can be applied into our problem. Similarly, there are two sets of parameters. We have model search space A parameterized by alpha and omega, and we have this implementation search space I parameterized by phi. So here I'm giving an example design space for a multitask learning search. We can try to decide how to design the neural network architecture for each task and try to decide when and how to fuse or to exchange information across two tasks. So this is the fusion operation. So we're trying to use these architectural variables to decide whether these blocks will be selected or whether these paths will be enabled. And at the same time, for the implementation search, we are trying to decide where each block will be mapped onto this heterogeneous accelerator here. So for example, for this block, there are 4 accelerators, and we want to decide whether it is mapped to accelerator 1 or 2 or 3 or 4. And this is decided by its mapping variable, these ones. So this is how we can formulate this co-design problem. Now let's take a look at how we're going to solve it. Based on this formulation, to solve the problem, what we need to do is to optimize the probability distribution of these probability variables by sampling and evaluating the possible architectures and mappings during the search. So this is because finally these variables will decide the final model architecture and the mapping strategy. We'll just pick the blocks and the paths and the mapping that has the largest probability. So now let's take an example. This is an example. After the search, within these 3 variables, this first one, the value is 0.7, the largest. So that's why we're going to pick up the first block and we'll abandon these 2. And similarly, if assuming that this path also has the largest value, so we pick up this path. So this is how we decide the model how does model look like. And similarly for the implementation, after the search, we can see that this value is the largest, so that's why we're going to finally map this block to the ACC3. So this is how we're going to decide what the architecture look like and what the mapping look like. Formally and simply, this is a co-design objective function that can be composed of different components. For example, the first one is the software loss, which can be the model accuracy, and the second one is the hardware implementation loss, which is quite flexible that you can actually define your own loss function. For example, the end-to-end latency, the power consumption, or the weighted sum. The key here is that these loss functions must be functions of the probability variables, either the model architecture variables or the implementation variables. This is because during the search, what we're actually doing is trying to update these probability variables iteratively through backpropagation, assuming that we're using gradient descent. And these probability variables will finally decide how we're going to choose the final model and the final implementation mapping. So actually, this is not hard, but there is one small problem, is that we cannot directly compute the gradient of these probability variables if we directly sample the model and the mapping for the evaluation. So what we can do to help is to use this technique called Reparameterization Trick. Maybe some of you have already known that. This exactly helps to solve this problem that the probability variables cannot take gradients. So assume that we have this original distribution, but we cannot directly sample from it. Otherwise, the gradient information will be lost. Instead, we simply sample a random variable from an unparameterized distribution, for example, just a 0-1 uniform distribution, and we can transform this random variable through a transformation function. So it makes it look like that we're sampling from the original distribution. The good thing about this transformation function is that it is parameterized by these probability variables. So now if we sample from this unparameterized distribution and we are computing the loss function, the probability variables are in the parameter space, so we can happily compute the gradients for them and update them. So this is how the reparameterization trick can help in this sampling procedure. And I would like to say that this is the beauty of this formulation, that it is really flexible and it can support different search spaces, different loss functions, and different objectives. So this is a very general and flexible formulation and framework. And this can help us to solve the hardware-software co-design problem, and you can actually adapt it for your own specific problem. So this is just a framework that you can borrow the idea. Okay, so this is the end of the software hardware co-design for MMT on heterogeneous platforms. And here are some interesting future works. First, of course, we can apply NAS for hardware-aware MMT model design, which I think might be the first step and can be relatively easier. And second, we can do it more aggressively using this nice idea to do simultaneous co-design, either use continuous optimization, as we already explained, using this probability distribution and sampling, or we can also use discrete optimization, such as some heuristics methods, which are also fine. Last but not least, here is there are some interesting direction that we care about is low power multimodal multitask learning. For example, on wearable devices, we really care about the power budget, and actually not all the modalities are available or active or necessary at all the time. For example, there are some technology called dynamic sampling of sensors trying to save some power. And similarly, not all the tasks are needed all the time. So we may also want to do a dynamic task choosing, scheduling, and mapping. So finally, this is the end of my talk. I hope it introduced something interesting and it can inspire some follow-up works in this exciting area. I really look forward to seeing more follow-up works, and of course, I myself will also dive into this interesting direction. So thank you very much for listening.